Okay, hi, I'm Inho from MIT, and today I'm going to introduce the Protego, which is an overload control enabling data center applications to achieve high throughput and low tail latency at the same time in the presence of the unpredictable lock contention. This is a joint work with Ahmed from Georgia Tech, and Saeed, Mohammad, and Adam from MIT. Servers in the data center can be overloaded by various reasons, including load imbalance, unexpected user traffic, packet bursts, or redirected traffic due to failure. When the compute is overloaded at the server, throughput degrades, and the latency increases significantly because of the receive live lock, where more CPUs are used for the packet processing and the request parsing, and less CPUs are used for application logic. To avoid congestion collapse and to ensure the request meets service level objective while providing the maximum possible throughput, overload control adjusts the incoming load by shedding it if the server is overloaded. Existing overload controls use delay signals from the different part of the systems as an overload signal because of its effectiveness and the fine granularity. For example, Breakwater and Dagger uses server-side CPU queuing delay, and SATA and ORCA use end-to-end latency as an overload signal. When the servers becomes overloaded, overload control adjusts the incoming load to the server, either by dropping the request with the AQM, or by admission control, rate limiting or signaling the request transmissions from the clients. So we tried to run our Lucene search application with the overload control, SATA, one with the end-to-end latency, and Breakwater, one with the server-side CPU queuing delay as an overload signal. However, the performance was far from what we have expected. For SATA, even though its tail latency is bounded, its throughput is far from its maximum. On the other hand, Breakwater achieves higher throughput than SATA, but its tail latency is unbounded. What went wrong here? In this talk, I'm trying to answer this question and propose a new overload control with a better congestion signal. In multi-threaded application like Lucene, each thread is handling a separate user request or a part of the user request. In order to keep the application state consistent with the multiple threads, each thread requires a lock to access the shared data. The locks in the data center application is often implemented with the blocking synchronization, like the mutex, because spin lock can waste the CPU cycles and degrade the performance, especially when the lock wait time is comparable to the duration of the critical section. When multiple threads need an access to the shared data at the same time, the lock protecting the shared data can be contended, leading high tail latency because only one thread is allowed in the critical section at a time. In this scenario, it's kind of trivial to handle lock contention, as overload control only need to take the queuing delay of the lock into account to determine whether the server is overloaded or not. However, to better utilize the concurrency with the multiple threads, the shared data is often divided into multiple pieces, each of which is protected by the different locks. With diverse data paths created by segmented shared data, when the locks becomes a bottleneck of the system, it becomes challenging to determine whether the server is overloaded by looking at the lock waiter queues. Specifically, it's not clear which queues to monitor and how to aggregate their queuing delay to determine whether the server is overloaded or not. To make the matter worse, as the required locks in the data path are determined by the application and the request state, it is hard to know which locks will be required in the data path in advance, and the bottleneck keeps changing depending on the workload, which leads to unpredictable lock contention inside the application. To demonstrate what happens with the lock contention in the application, let's take a simple example with the two data paths, blue and red. Each data path requires an access to the exclusive shared data protected by different locks. And when application receives the user request, the request handling thread takes either blue data path with the 20% of the probability and the red data path with the 80% of probability. When both data paths are not saturated, the throughput of each data path increases linearly as overload increases, while the tail latency stays low. If we further increase the overload, red data path becomes saturated, and its throughput does not increase further, while its tail latency starts to increase due to the delays waiting for the lock. In the meanwhile, because blue data path is not saturated yet, its throughput keeps increasing, and its tail latency is still bounded with an increased overload. As a result, there exists a misalignment in operating points to achieve high throughput and low tail latency. If an overload control uses an end-to-end latency as an overload signal, like the SATA or ORCA, it will throttle incoming load as soon as one of the data paths becomes congested, leading to low latency, but low throughput. On the other hand, if an overload control uses a server-side CPU queuing delay, like the breakwater or dagger, it will not take any effect before CPU becomes the bottleneck, leading to high throughput, but high latency. In the presence of such a lock contention, how could we achieve both high throughput and the low tail latency? In this work, we proposed Protego, an overload control to achieve both high throughput and low tail latency, even for the application with the unpredictable lock contention. Protego is composed of the two key components: active synchronization queue management, or ASQM, which ensures low latency for all the data paths in the application by dropping the request, and performance-driven admission control to achieve high throughput with efficient use of the hardware resources. Let me dive into the details one by one. With the unpredictable lock contention, the only way to achieve both high throughput and low tail latency is to drop the requests that are expected to wait for a lock for a long time in a congested data path. To realize the request drops in the congested data path, we developed ASQM. In ASQM, when a request arrives at the application, it is assigned queuing delay budget, which represents the maximum amount of the queuing delay it can accommodate to meet the target latency. Queuing delay budget is computed by subtracting 99 percentile service time and the 99 percentile network latency from its target delay. When a request needs to wait for a lock, it first checks whether its queuing delay budget is larger than the queuing delay of the lock waiter queue, and if so, it enqueues the request into the queue. Otherwise, it drops the request and delivers the failure message to the client so that the client can decide what to do with the dropped request. For example, the clients can discard it and degrade the service quality or retransmit to another hopefully non-overloaded replica. When the request successfully grabs a lock and dequeued from the lock waiter queue, its queuing delay budget is decremented by the actual queuing delay it has waited. To handle the CPU congestion, ASQM treats the CPU thread queuing delay in the same way as the lock waiter queue. So let's take a look how the application performance has changed with the ASQM, with the previous example with the blue data path and the red data path. In the bottom, it shows the throughput, 99 percentile latency, and drop rate. Here, I set the target delay as 200 microseconds, considering the processing time. When the overload is small and none of the data paths become congested, throughput grows linearly, while tail latency grows marginally due to the occasional request bursts. As none of the data path is congested, ASQM does not drop any request. If we increase the overload further, the part of the data paths become congested. As a result, throughput grows sublinearly because only uncongested data paths contribute to the additional throughput. Because of the increased queuing delay in the congested data path, tail latency increases and the ASQM starts to drop the request. In this partially congested stage, with the blocking synchronization like the mutex, CPU is not still 100% utilized because the threads waiting for the lock is blocked and not consuming any CPU cycles. Going beyond the partially congested stage, finally, all the data paths become congested if we increase the overall load further. In this totally congested stage, throughput does not increase anymore since all the data paths are saturated, and the tail latency and drop rate still go up with the increased queuing delay and the size of the request bursts. This totally congested stage continues until the CPU becomes a bottleneck of the system. If the overall load increases even after the CPU becomes decongested, the throughput starts to decrease, and the tail latency further increases as the system enters into the live lock state. With this throughput and the tail latency behavior, in order to achieve high throughput and the minimum SLO violation, the overload control should bound the incoming load in the right-hand side of the partially congested region marked as a red circle here. Then, which overload signal should we use to effectively operate the server in this region? We paid attention to the throughput behavior inspired by the natural congestion control, like the PCC or BBR. First, we defined the efficiency metric, which is measured by the number of responses sent divided by the number of requests received at the server over a small time frame. Efficiency number represents how much of the incoming requests contribute to the actual throughput. In partially congested stage, the efficiency value is between 0 and 1. Protego uses efficiency value of the 10% by default, but the service operator can specify different target efficiency value based on their target metric, such as 0 drop rate or highest possible throughput. With specify the target efficiency value, Protego measures the efficiency for every 4 end-to-end RTTs. If measured efficiency value is larger than the target efficiency, it admits more load, moving the operating point right-hand side. Otherwise, it reduces the incoming load, moving the operating point left-hand side. With this control loop, Protego tries to operate the application with the efficiency value near the target. To evaluate the Protego, we constructed testbed in Cloud Lab, and for evaluation, we defined a metric called throughput that represents the throughput of the responses whose end-to-end latency is less than the target delay. Throughout the evaluation, we answered 3 key questions. First, does Protego achieve high throughput and low tail latency under the unpredictable lock contention? And second, how fast the client is notified with the rejected request? And finally, how the request drop affects the end-to-end latency. We compared Protego's performance with the 2 existing overload control, breakwater and SETA. Breakwater is a credit-based overload control with the CPU thread queuing delay and the packet queuing delay as a congestion signal. And SETA is an adaptive overload control for a staged event-driven architecture, which rate limits the clients based on the measured end-to-end latency. First, we consider the Lucene search application that we have seen earlier with the COVID-related tweets over 3 days. To measure the performance of the Protego, SETA, and breakwater, we generate the load from the 1,000 clients. Each client generates the search query based on the word distributions in the tweets. As SETA modifies a client's request sending rate based on the end-to-end latency, it achieves bounded latency, but its throughput is limited. Because breakwater uses server-side CPU queuing delay, it does not throttle the incoming load at all, and it achieves very low throughput because of the very high latency. Thanks to the ASQM and the performance-driven admission control, Protego achieves about 3 times larger throughput and 12 times lower tail latency compared to SETA by dropping about 20% of the request. Then, how the dropped request affects the end-to-end latency. To demonstrate the impact of the request drop on the server-side service-level end-to-end latency, we considered the following setup. First, a client issues a memcache request from a set-heavy bar workload to the server 1. And if the server 1 rejects the request, the client retransmits the same request to the server 2. With this setup, we measured the throughput, failure delivery latency, and end-to-end latency with the different clients' demand. We set the target delay for a single server as 100 microseconds, and service level objective as twice, considering there is a maximum 1 retransmission in this setting. When server 1 is not congested, the throughput of the server 1 increases linearly without any failure message from the server 1. The tail latency increases a little as the client's demand increases due to the increased log queuing delay, but it is still less than the target delay. If we increase the client's demand further, the server 1 starts to drop the request, and the client receives failure message. Because ASQM drops the request if the queuing delay budget is not enough compared to the queuing delay, failure delivery latency is shorter than the single server target latency. As dropped request is retransmitted to the server 2, another round-trip time to server 2 is added to the end-to-end latency, but it is still bounded, still less than the service level objective. Thanks to the retransmission, the aggregated throughput by server 1 and server 2 grows linearly as the client demand increases. Okay, let me conclude the talk. Protego is an overload control designed to handle unpredictable lock contention in the data center applications. With active synchronization queue management and performance-based admission control, Protego achieves high throughput and low tail latency, on-time failure delivery, and effective scaling to multiple machines, even in the presence of unpredictable lock contention. We believe that our approach can be further extended to other types of the application bottleneck, including the blocking I/O. Thank you, and I'm happy to take any questions.